Hello everyone, my name is Wuli Zuo and I'm majored in computer science. Today I will talk about my course project, the literature review on web content crawling and indexing. I chose this topic for the following reasons. First, I am really interested in web search engines, but knew nothing about them before this project. So I treated the project as a very good opportunity to get started. Second, the web search engine is one of the major businesses of my favorite internet company, Google. And third, I have heard that the early work of the Google founders are very excellent and worth reading. Regarding to this, I have to tell you that's true. If you are in a similar situation as I was, I strongly recommend you to read those papers. In order to have a more comprehensive understanding, I decided to do this project individually. This is my outline for today's presentation and also the structure of my literature review. I will start with a brief introduction of information retrieval and the architecture of web search engines. After that, I'll review the work on strategies of web crawling and then indexing. Finally, I'll give my conclusion. Okay, let's begin with the introduction. Searching for information on the World Wide Web is a daily activity for most computer users. To improve search effectiveness and efficiency, and to provide more meaningful information to users, researchers working in the field of information retrieval are trying to come up with faster and simpler approaches to obtain the right information. Information retrieval is defined as a field concerned with the structure, analysis, organization, storage, searching, and retrieval of information. So searching the web is by far the most common application involving information retrieval. Due to the astonishing growth of the World Wide Web, people have to rely on web search engines such as Google and Yahoo to obtain their desired information. There are some work focuses on the architecture of search engines. Callan's work in 1994 gives a systematic overview of an early general-purpose search engine. Brin and Page describe an early version of Google or web search engine architecture in their work published in 1998. Hatcher and Gospodinetti comprehensively describe the Lucene architecture and components. Here is the typical architecture of a modern web search engine. It has two major functions, the indexing process and the query process. The indexing process builds the structures that enable searching, and the query process uses these structures and the user's query to produce a ranked list of documents. There are 6 components: a crawler, an indexer, an index file database, a query parser, the ranking mechanism, and the user interface. This general design has proven to be useful, and many of the components have been used for decades, among which the crawler and the indexer are 2 very critical ones. So my survey focuses on crawling and indexing by reviewing more than 70 pieces of related literatures in strategies and technologies of web content crawling and indexing. In the rest part of my presentation, I won't go details into each strategy, but will select some quite representative ones to introduce. A web crawler, also called a spider, is a program that downloads web pages in an automatic manner, and this process of automatically finding and downloading web pages is called crawling or spidering. According to the technology of implementation and the system structure, web crawlers can be classified into different types, including general purpose, focused, incremental, deep, and distributed web crawler. We should notice that in practice, the realization of a web crawler system is usually the combination of several of the above crawler technologies. General-purpose web crawlers are also called scalable web crawlers. The object of general-purpose crawling is extended from a few torrent URLs to the entire web. The aim is to collect data mainly for search engines or portal websites and web service providers. Most web search engines are based on early generation crawlers and rely heavily on graph algorithms. So the certain crawling strategies adopted by general-purpose web crawlers are some graph strategies, such as depth-first and breadth-first strategy. Depth-first strategy follows each possible path to the end before another path is tried. And breadth-first strategy crawls the page according to the depth of the web content directory level. A focused web crawler attempts to selectively crawl only those web pages that are related to a given set of topics, rather than having to explore every web page. The most relevant or important web pages have a higher priority to be downloaded and to be put on the front of the priority queue. Link evaluation and content evaluation modules are added in focused web crawlers. Different strategies calculate different importance and result in different access orders. These strategies are usually based on keywords, link semantics, or data mining technologies. Fish search is a text similarity calculation method. It takes the user's query words as the topic and considers the page that contains the query words is related to the topic. The limitation is that it does not evaluate the correlation degree between the page and the topic. Shark search is an improvement of fish search. It uses a spatial vector model to calculate the relevancy between pages and topics. The priority of the URLs depends on various factors. Google algorithm uses 4 importance heuristics to order the page: similarity of a page to an input query, backlink count, page rank, and location metric. Their experiments show that important pages can be obtained faster by a crawler with a good ordering scheme. Hits is another important strategy based on the web structure. Later, we will see Google algorithm and hits again more than once. The concept of intelligent crawling is introduced in 2001. It learns characteristics of the link structure of the web while crawling and uses this information to estimate the probability that a candidate is useful for a given crawl. In order to keep track of the rapid changes on the web and keep the web page documents stored in the local repository synchronized with the live copy, some crawlers incrementally update their indexes and local collections. After the collection reaches its target size, the crawler can continue to access the pages to update the local copy incrementally. Through this incremental way of updating, crawlers can refresh the existing pages and replace pages of less importance with the new and more important pages. Such a crawler is called an incremental crawler. The research on incremental web crawler attempts to come up with more efficient refresh strategies. An important approach is the sampling-based method. This method is widely used to detect web page changes. In this algorithm, a few web pages are downloaded as samples and then used to find the websites that contain most changed pages in order to allocate more resources to these websites. The sampling is operated at the website level using a greedy policy. One of the authors, Zhou, is an excellent Chinese scholar who has worked with Google founders on the search engine. I especially like his papers. Most of them are written beautifully, with comprehensive experiments and clear conclusions. Due to the increasing of both web content and the complexity of web structure, a large amount of web pages lie in the deep web or hidden web. Usually, these pages can only be obtained by submitting query to the database. Deep web crawlers are such programs used to target deep web content. Different strategic approaches of deep web crawling have been proposed. Some strategies try to improve the query form submitted to the database. Others explore some graph algorithms such as storm tree to obtain more efficient crawling. The one I like to introduce here is the grid-based middleware named Open Grid Services Architecture. It supports basic functions for simply using and ideally computing resources and crawling the deep web. This middleware is useful for developers who may have little knowledge about how to use ideal and distributed computing resources, and enable them to easily implement a grid-based deep web crawling system. A distributed web crawler is a kind of software that uses distributed computing technology. By taking the advantage of the internet, search engines use multiple machines to operate their crawling tasks to increase the throughput. I classify the approaches for distributed web crawlers into three groups: scalability-based, system structure-based, and other approaches. UbiCrawler is a scalable distributed web crawler. Its features include platform independence, linear scalability, and graceful degradation in case of failure. It uses an effective, consistent hash-based assignment function to partition the domain for crawling according to the host components across crawling machines. Nasri and his co-authors propose a model-based distributed web crawler. This architecture is based on the UbiCrawler. It uses stochastic networks to model the crawling, and the Mobius tool is used to design the distributed web crawler in the stochastic networks. Another quite impressive method is called UniCrawl. It is a geographical distributed crawler that minimizes the inter-site communication costs. UniCrawl arranges a variety of geographical distributed sites, each operating a separate crawler, and relies on well-developed techniques to obtain and parse the web content. UniCrawl separates the crawling domain space to each site that compromises a sequence of MapReduce tasks and integrates their computing resources and storage. Here is a summary of web crawling strategies. We can see that each type of crawler has its unique aspects to improve crawling. Now let's move to indexing. Indexing is about how queries are processed by a computer. When we talk about indexing in the context of web search engines, it refers to as a process designed to extract content of web pages. Web indexing is all sorts of methods for indexing the content of a set of websites or of the internet as a whole. Web search engines mainly focuses on the full-text indexing of online natural language documents. The indexer module in a search engine builds various indexes on the collected web pages. The text index and the link index are two basic types, and we can use these two types and web pages to build a variety of other types of useful indexes, such as the utility index. Text-based retrieval is the main method to identify web pages that are relevant to a query. There are some quite traditionally used methods to implement text indexes, including suffix arrays, signature files, and inverted files or inverted indexes. Inverted indexes are traditionally the choice for the index structure of the web. In order to build link indexes, we usually model the web or the portion that we want to crawl as a graph. We model each web page as a node in the graph, and we treat a hypertext link in one page pointing to another page as a directed edge from one node to another. A link index structure should be an efficient and scalable representation of such a graph. Neighborhood information is the most common information to build link indexes. Some people explore strategies to provide this information more efficiently. Utility indexes are established by the analysis of the page collection. They are typically used at query time to support the ranking of search results. Google's PageRank is a link analysis and ranking scheme. It assigns a weight to each page to measure its relative importance, and a hyperlink to a page is viewed as a vote for support. The rank page score of a web page is defined recursively. It is based on the number and the PageRank metric of all the incoming link pages that points to it. So a page receives a higher PageRank score itself if it is linked to by many other pages with high scores. The HIT algorithm is another link-based algorithm. For a given search query, it identifies a set of authority pages and a set of help pages, calculates the authority weights and help weights to determine the visiting order. This algorithm is used by Chalma and Ask. Now we will take a little while to review some early work on the inverted index. Since it is the index structure adopted by most search engines and is at the core of all modern web search engines, and is considered as the most flexible and efficient index structure. A work conducted by Zuo gives a comparison between signature files and inverted indexes, and concludes that the space consumption of inverted indexes is lower than that of signature files, and the efficiency is higher. And also, inverted indexes are relatively simpler to implement. We should know that indexing is not a new concept of the web. Actually, early work on inverted indexes for text retrieval methods was developed for databases. Different design schemes for inverted indexes have been proposed to achieve better balance among costs, space consumption, and query evaluation. Shelbo is one of the first who considered inverted indexes designed for text. He argues for the use of special-purpose hardware enables rapid merging. Zuo and his colleagues investigate the layout of lists on disk and the management of short lists with blocks. Two main processes of indexing are index construction and index maintenance. There are other processes or topics related to indexing, for example, compression techniques and ranking-motivated index choices. Many of them have strong correlation with the ranking mechanism, so I prefer to discuss those topics in another paper on the serving process of web search engines rather than in this one. This work only focuses on index construction and maintenance. An index must be created from the text collection before it is used for query. Researchers have conducted much work to explore more efficient algorithms for index construction. One classical way is the two-pass method. The first pass records various statistic data of the document library. This information is just used to allocate space for the inversion list of each index entry, and the inversion list of the document is not constructed. The second pass uses the information obtained from the first pass to allocate sufficient disk space to store dictionary files and inversion files. An innovative approach is the single-pass inversion method. It does not require the complete vocabulary of the indexed collection in main memory. This approach can operate within limited resources without sacrificing the speed. Maintenance or dynamic update of inverted indexes is a basic requirement. There are some common strategies include approaches such as rebuilding and merging. Much work in this field has been done and targets different aspects. Cutting and Pedersen are pioneers who first examined the problems posed by updating text indexes. They point out that B-trees are an effective tool in implementing indexes. They present novel merge update approaches that perform better than straightforward block update and reduces space requirements without sacrificing performance. Cutting and Pedersen make some practical recommendations, such as the need to make updates in batches rather than term at a time or document at a time. These recommendations are still relevant nowadays. There is an critical evaluation research. Lester, Zobel, and Williams experimentally evaluate different strategies for index maintenance, including in-place and remerge, in the process of insertion under the requirement that inverted lists remain contiguous on disk for fast query evaluation. The finding of the experiments of large volumes of web data is that in-place update is more suitable when the memory buffer size is limited or the insertion rate is low, while remerge is the fastest approach if large buffers are available. Here is a summary for indexing. We now know that there are two basic types of indexes, the text index and the link index. And inverted indexes are at the core of modern search engines. We notice an impressive method, PageRank, which is a global ranking scheme using linked indexes. We find that techniques in index construction and maintenance attempt to better balance cost, space consumption, and query evaluation. So, come to our conclusion. By reviewing the literature of web crawling and indexing, we can conclude that each web crawling strategy supports some unique features, which is helpful to describe various relationships and promote crawling performance, and that the inverted index structure is at the core of modern search engines, and current research directions are often related to efficient way of index construction and maintenance, as well as innovative evaluation methods. In a commercial search engine, the crawler should have the incremental ability, be capable of scaling in a distributed environment, and be able to retrieve information from the deep web besides the hyperlinks. And the indexer should be more efficient to sacrifice the requirements of ranking so that the query results could be served to the user with better and more personalized experience. The ultimate goal and the future scope for this field of work will be a robust and efficient service which can provide myriad capability. And here are my references. Finally, I would like to express my thanks to Mr. Jilei Wang, who is a Google engineer, for his help when I first thought about this topic. He explained to me the working principles of web search engines and the workflow of Google, which helped me to gain a basic understanding of the topic and gave me confidence to explore this field. Thank you for listening. Have a great day.